Hi everyone, my name is Fangyi Yu. I'm currently a postdoc at Harvard. Today I'm very glad to share one of my work with you. It's two strongly truthful mechanisms for three heterogeneous agents answering WINE questions. This is a joint work with Grange and Beck. So the problem that we are interested in is information elicitation without verifications. A lot of time we try to collect signal, opinions, information from agents, but we have no way to verify whether they are telling us the truth or not. So for example, we may be interested in whether they are happy about our conference or do they like certain restaurants. Those informations are subjective. It will be very hard for us to have a ground truth available to check that. On the other hand, we can also add something like their private information that is only available for themselves. For example, what is their commute times, or what is their usage, the usage time of their cell phones. In this line of work, we're trying to design mechanisms to incentivize agents to report truthfully. So the idea is that it will be possible to use peers' report to incentivize agents' truthful reports. And the main idea is that a lot of times agents' signals are dependent. For example, if we're trying to collect the commute time from agents like Alice, Bob, and Charlie in this plot, we know that they may share some route, even though we do not have the information about, we cannot know their exact commute times. But if we know, for example, Charlie's have a very long commute times, and because Alice have a lot of intersections, common route as with Charlie's, so we know that Alice's commute time may be large as well. On the other hand, Bob's commute time is very different from Alice, so maybe their commute time will be negative correlated. So the idea is that we can use others' reports to verify and check whether Alice is telling the truth or not. So in this work, we are thinking about we can collect agents and ask them to report their own signals or their predictions on others. For example, we can ask what is the Bob's commute times, and we can also ask Alice what is her predictions on Bob's commute times. So our main contribution of these papers is that we propose two differential peer prediction mechanisms that is strongly truthful. So that is truth-telling is highly rewarded in our mechanisms. First, the truth-telling is strict Bayesian-Nash equilibriums. That is, if everyone else is truth-telling, then the best response for an agent is to tell the truth as well. Second, we ensure that truth-telling will pace strictly higher than any other equilibriums. So for example, we try to avoid that agents collude with each others and they may report the same signal, or they randomly report some noise to the systems. In our mechanism, we ensure truth-telling's total payments is higher than all those kind of equilibria. However, there's a caveat, that is, because our mechanisms do not have ability to verify that, so it will be impossible for so the agents may collude with each others and they can relabel their reports. For example, if they observe a blue signal, then they can always relabel it and report red instead. And it will be information theoretically impossible for us to distinguish those relabeling strategy. So our mechanism is indeed strictly higher than any other equilibria, except those permutation equilibriums. And our mechanism works in a very general setting. First, we only require 3 agents. So in this talk, we will call them Alice, Bob, and Charlie. Previous will kind of need more of them. For example, need 6 in a disagreement mechanism, or infinite number of agents in a basic interest theorem. And in our mechanism, we also collect minimal information from agents. So each agent only have a single item report. That is, agent only need to report their signal or their predictions on other signals. And finally, our mechanism work on very general priors. So they can be asymmetric, continuous, or which is very generous compared to previous mechanisms. Finally, our mechanism is prior-free. That is, our mechanism does not need to know the joint distributions of agent signals. Okay. So this is the outline of the rest of the talk. There are 3 parts. First, we are going to review proper scoring rule. In particular, investigate some special property of log scoring rule and its connections to information theory. For the second part, we are going to briefly talk about how to use proper scoring rule in information elicitation without verifications, and then propose our 2 mechanisms and hand-waving about why those mechanism works. And finally, we are going to talk about the connection to previous work, in particular basic interest theorem. Okay. So the first part, let's talk about how can we elucidate predictions when we have when verification is possible. So the settings goes as follows. We have a joint 2 random variable W and A, join this and perform P. W is the random variable that we are interested in. For example, we will call it the ground truth. For example, whether tomorrow is going to rain, or what is Bob's report. And A is Alice signals. So here there's an expert Alice who has a privately observed private signal A, and with these informations, Alice can make better predictions on the ground truth. And how can we design a function to incentivize Alice to make her best reports? So a scoring rule, which is a mapping from the ground truth and Alice predictions to a score. And a scoring rule is proper if honest report will maximize this score. So in this case, Alice should report her posteriors on the ground truth if she wants to maximize the score. Okay. And so let me make sure that we're on the same page, and let's clarify the process. So the process goes as follows. We first announce a scoring rule that we are going to use, and then Alice observes a private signal A, and then Alice reports her prediction P, which may not be a truthful report. And then we see the ground truth revealed, and we pay Alice by the scoring rules apply on the ground truth and her predictions. One special case of the scoring rule is the log scoring rule. So it will be just the log of Alice's predictions on the revealed ground truth. So in this case, ideally you should put a higher. To maximize the payments, Alice report prediction should put higher weights on the ground truth, on the state that have higher probabilities. So this log scoring rule has 3 properties. First is a proper scoring rule. That is, we can use that to incentivize truthful reports. Second, the expected score is actually the Shannon mutual information. So here the randomness is the expectation is taken over the ground truth W and added signal A. And this would be just the Shannon mutual information between the ground truth and Alice's private signal A. So the third property is more complicated. So let's consider the following settings. Instead of having a single signal, we consider Alice have a sequence of private signals, which are jointly sampled from some distributions. And in this case, we ask Alice to make her prediction whenever she got a new signal. So Alice first report P1, which is her prediction when she knows the A1, and then P2 when Alice observes A2, and then Pi when Alice observes AI. And the prediction of Pi should be the posteriors of the ground truth condition on all the signals from A1 to AI. And in this case, the expected prediction scores difference will also have a nice connections to information theory. So here the prediction score of Pi minus the prediction score of Pi minus 1 would be the mutual informations between W and AI conditioned on all previous signals. And this chain rules is very special and is not true for other proper scoring rules. So in summary, we are going to use these two properties to design our peer prediction mechanisms. First, the log scoring rule is proper, so we can ensure that truth telling will truthfully reported predictions will maximize the payments. Secondly, you have this chain rule property, and this is already discovered, for example, in Kong and Shannon-Beck's mechanism illustrate that. So now we are ready to talk about our mechanism. Before talking about that, let's think about how can we use proper scoring rule in the mechanisms. Okay. So in our mechanisms, we say that we ask agents to play one of these three roles. The first one is an agent can be the target. That is, the target is asked to report his signal, and we are going to use his report as the ground truth, and which is going to be predicted by others. An agent can also be an expert who makes predictions on the target signals. So in this way, it's quite nature that using proper scoring is a very nature setting. Finally, an agent can act as the source who provides information to the experts and help the expert to make better prediction on the targets. So in our differential peer prediction mechanism, we are going to ask the target, Alice, Bob, and Charlie, to act these three roles in our mechanisms. Okay, so we have two mechanisms, and these two mechanisms have basically the same procedures, but they have different way to pay the agents. So the common procedures goes as follows. We have Alice, Bob, and Charlie. We first ask Bob and Charlie to report their signals. Okay, and then we randomly select one of it as target and the other as the source, uniformly at random. And then we ask Alice to be the expert. We tell Alice who is the target, and ask her to make predictions on the target signals. And then we tell Alice who is the source. We let Alice know the source's report and ask her to update her predictions on the target signals. So here there's two predictions. The first is initial prediction, the other is the improved predictions. Okay, so to complete our definition, we need to define our payments. So for the source differential peer prediction mechanisms, the payments goes as follows. Suppose we let Bob is the target, and vice versa. So if we set Charlie to be a target, everything will focus. So when Bob is the target, we pay Bob 0. In this case, truth telling will not hurt Bob, but it's neither a strict best response for Bob, as truth telling could be. And then we're going to pay Alex by the sum of her prediction score. That is the score on the improved prediction and the score on the initial predictions. Because the log scoring rule is proper, so Alex is incentivized to report both predictions truthfully. Finally, we can pay Charlie's by the improved score, that is the score on the improved predictions. And again, because log scoring rule is proper, and Alice is going to make her best prediction, so it will be best off for Charlie's to report her signal truthfully. So in this case, we can make sure that Alice and Charlie are going to their best response is the truth telling. And for Bob, because we randomize the roles between target and source, so Bob would be the source with probability half. So Bob is also strictly prefers truth telling and truth telling equilibriums. And this completely proof that truth telling is a strict Bayesian Nash equilibriums in our source DPP mechanisms. Okay, so let's step back a little bit. In our source DPP mechanism, what we do is we use the fact that log scoring rule is proper, and we can ensure the expert and source were trying to report truthfully. And we basically ignore targets incentives there. Okay, to complete our mechanism, we also need to make sure our source DPP mechanism is strongly truthful. That is, truth telling will pay strictly more than all the other equilibria. So instead of paying Charlie's the improved score, we minus 3 times of initial score prediction score. This will not affect Charlie's incentives because Alice's actions cannot affect the initial prediction score. And by doing this, we can make sure the total payments would be the difference between the improved score and the initial prediction score. And as we mentioned, by the chain rule of the log scoring rules, the expectations were equal to the conditional mutual information between Charlie's signal and Bob's signals, conditional on Alice's signals. So by data processing equality, we can make sure that truth telling will pay strictly more than any other equilibrium, Okay, so this covers our source DPP mechanisms. Now let's talk about the target DPP. So for the source DPP, we make sure the source is incentivized to report truthfully. For the target, we're trying to make sure the target also incentivized to report truthfully. Okay. However, this is not very easy. It is not just a direct result from the proper scoring rules. The proper scoring rule only ensure that if you the truthfulness happens in the second argument. That is, the expert and source will try to make their predictions as accurate as possible. However, if we want to incentivize the targets, we need to make sure that the first arguments of the proper scoring rule or the scoring rules also incentivize truthful reports. This is not directly. This cannot be directly derived from the definition of proper scoring rules. So our observation, or our main observation in this paper, is that the log scoring rule can be actually used in the reverse way. So as we mentioned that the log scoring rule on the predictions, improved predictions and initial predictions, this difference in expectation will equal to the conditional mutual informations between the target signal and the source signals. And it has these symmetric properties. So indeed, if we pay the targets this difference, the targets also incentivized to report his signal truthfully. So we actually prove that we actually prove this formally by very basic calculations, and we can show that if we pay Bob or the targets by this difference, then Bob's best response is also report truthfully. So to summarize, our target DPP payments goes as follows. Suppose, again, Bob is the target. The NS, the expert, get the sum of the score, which is similar, identical to the source DPP. And then we pay Bob's the difference, that is the difference between improved score and the initial predictions. And by our main observations, Bob is strictly preferred to tell the truth at a truth-telling equilibrium. Finally, we pay Charlie's -2 of initial score, and because Charlie's behavior does not affect his payments, so truth-telling will not hurt Charlie's utility. And because we randomize the roles of source and targets, Charlie also strictly prefers truth-telling as well. Finally, for strongly truthfulness, the total payment is identical to the source DPP mechanism, so they are going to the truth-telling is going to pay the highest among all equilibriums. So here is a recap or comparisons. In our mechanism, we use two disjoint set of ideas. The first is target incentives. We're trying to make sure the target is incentivized to report truthfully. The second is the source. We're trying to ask the source to do so. So to make sure the target report truthfully, we pay the target the difference. And that is the difference between improved score and initial score. And for the source, we just use their informations to improve the predictions and pay the source by the improved score. So they have pros and cons in this two approach. For the targets, it seems like it only applies to the log scoring rule. In our latest versions, we show that, for example, quadratic scoring rule does not have these properties. The good part, the pros of this idea is that it's kind of more parallel. We are going to illustrate this later in our Bayesian truth theorem. And for the source incentive for the source DPP, it works for all scoring rule as long as it's proper. However, it requires a sequential process. That is, you need to derive improved predictions using one agent's signals. Okay, so let's briefly discuss how to use these two ideas to understand previous mechanisms. So let's first talk about Bayesian truth theorem. This is proposed by Perlak, which might be the first mechanism for this pure prediction without verifications in the detail-free setting. So let me give you a very brief summary. The mechanism collects each agent's signals and their predictions on others' signals. Okay, and then for the prediction score, you're trying to make sure agents make their prediction accurately, truthfully, you can use log scoring rule to pay those agents. And then the difficult part is trying to incentivize agents to report their signal truthfully as well. And what they do is very similar to our target DPP. They actually pay a difference between two predictions, two prediction score. The first is they collect agents' signals and calculate and aggregate predictions. And on the other hand, you also use one agent's predictions, and the BTS pay the signals by the difference of these two prediction score. And by making assumptions on symmetries of agents and infinite number of agents, they can indeed learn these improved predictions through agents' report without actually asking them. So this kind of decompose this sequential process and make the process to be parallel. For the source incentive mechanism, this is a more straightforward ideas, and there's several previous work used this one. For example, the robust BTS by Vygotsky and Parks. They basically use S agents to report their predictions and their signal, and they can use one agent's signal to improve another agent's predictions, and using that to reward agents' truthful report for truthful reporting their signals. And later on, Zhang and Chen have a knowledge-free peer predictions, and in their mechanism, they relax the symmetry assumptions on robust BTS. Okay, so this finish my presentations, and I'll be very happy to discuss with all of you. And if you have any questions, just ask me. Thank you.